So I was given the assigned trial lecture title of Large Igneous Provinces and Mass Extinctions, Association or Causality. This is sort of a big, broad question that is subject of much ongoing research and debate. And so because it's such a broad topic, I won't be able to address every aspect of this morning, but I would like to provide sort of a framework in which we might be able to start addressing this question and look at then some case examples, mostly from the end Permian, sort of to try to answer this question. And hopefully this will also provide some background for those of you that aren't as familiar with these large igneous provinces and mass extinctions, so that you can have a better understanding of my defense lecture later today. So it's a bit more of an introduction to the subject. So I'd like to start with this plot by Cordio that shows the remarkable correlation, as he puts it, between the age of large igneous provinces and mass extinctions. The idea is that the ages of continental flood basalts and oceanic plateaus are here in the dots with the labels on the top. And you can, for each of these events, correlate them with some sort of boundary event, either a mass extinction or an ocean anoxia event. If we look at specifically only the last 300 or so million years of Earth's history, we can correlate these lip events, as we call them, with boundary events. However, if we think about it from the mass extinction side, if we look at the entire Phanerozoic, not just the last 300 million years, of the 15 Phanerozoic extinctions, maybe only 6 coincide with major episodes of volcanicity. And the ocean anoxia events that we see are associated with major, minor, and no mass extinctions. So while maybe there are mass extinctions for most of the large igneous provinces, there are not necessarily large igneous provinces that correspond to all the mass extinctions. And so it's not really clear that there is a sort of a one-to-one correlation between these two events. So this leaves the question still, is there a causal link between large igneous province formation and mass extinctions or not? As we know, correlation does not imply causation. But as XKCD points out, correlation does waggle its eyebrows suggestively. And it gives us sort of a starting place and a sort of first starting point to look at. So to tackle this question, I would argue that we start with this. I'm sorry, I just saw it all over here. That's really great. Okay, so the key, I think, maybe to tackling this question is to sort of try to look at a framework. And I think perhaps the key to distinguishing between association and causality is determining mechanistic pathways. Many things can be correlated, but of course it doesn't necessarily mean that one thing causes the other. However, if we can find a reason that one thing causes the other, we might be able to make the link. First off, I would say we should look for correlation, because without any correlation, causality is much less likely. Are there then plausible causal mechanisms? Is there a way for this event to be caused? And thirdly, do we have evidence for any of these mechanisms actually occurring? And fourth, is there, on a sort of a very fine scale, this temporal cause-effect relationship? So if we have multiple potential causes, did the effects that we would expect, do they appear always after the mechanism occurs? So I'll use this to address this question. So applying this to this question of large igneous provinces and mass extinctions, I'm going to provide a little background for you on mass extinctions. What are they? What could possibly cause them? Large igneous provinces, also, what are they? What are the environmental implications of these? Then looking at this sort of case study, applying these 4 questions to this problem, and using the end Permian as an example. So mass extinctions, what are they? So life began on Earth about 3.5 billion years ago. If we look at this column here as all of Earth's history, life began maybe roughly about here. This is the beginning of Earth, and this would be today. And so for most of Earth's history, life sort of existed as cyanobacteria or chemoautotrophs, most likely, looking something like this in the Earth's oceans. And then starting about 600 million years ago was the Cambrian so-called explosion, where life really diversified and became known as what we see today. So if we expand this little section up here, we've now divided this into the most commonly known geologic timescale. And if we look at the number of families in existence based on the fossil record of the last 600 million years. This is the pattern we see, with like a pretty steady increase in the number of families and increasing diversity. And we see, though, that there is some sort of faunal evolution. Could be divided into these three different faunal groups. And we see sort of then the evolution of life through time. If we look more closely at this fossil record, we see that the abundance of species actually sort of waxes and wanes throughout time on a very fine scale. So here we're looking at cephalopods, and we see that the width of this line represents how abundant they are in the fossil record. We see it gets wider and thinner throughout time, and that's a normal process, and also that these lines begin and end sort of throughout time. And this is normal evolution. This is the origination of species and the extinction of species, which happens at a constant background level throughout time. However, if we return to this Raup and Sapkowski plot, we see that there are places where this isn't just a smooth trend of increasing diversity. We have these sort of downward drops, sudden downward drops. And these are what we refer to as mass extinctions. So there are times when the extinction rates surpass speciation rates. And if we focus on the biggest of these 5 drops, they've been named the big 5 mass extinctions. We basically have the end Ordovician, the late Devonian, the end Permian, which is what I'll be talking about later today, the end Triassic, and the Cretaceous Tertiary, the latter being sort of the most famous amongst the public, the extinction of the dinosaurs. So what could possibly cause these extinction events? Why does life suddenly, why do extinction rates sort of skyrocket very suddenly at certain points in time? Well, there have been a number of proposed triggers, some crazier than others. But this is sort of a summary of some of the most maybe popular, most discussed extinction mechanisms. So I'll be talking about volcanism mostly today, but there's also meteorite impact, cosmic rays, Milankovitch cycles, and supercontinents. So to skip over volcanism for now, because I'll come back to that, the idea of impact-induced mass extinction was really popularized by Alvarez for the KT boundary event, the dinosaurs. And this was because they found this iridium anomalies, shocked quartz, and then finally the Chicxulub crater on the Yucatan Peninsula, which really brought all this evidence together. The idea being that you get a lot of shocked quartz when you impact something very hard into the Earth's surface, and the iridium comes from sort of this extraterrestrial material where it's enriched, and then gets deposited in this abnormally enriched layer globally around the world as the dust settles. And the effects of an impact you can probably imagine, but they include habitat destruction, certainly right where the impactor hits, and in any ejecta zone. Then you also get aerosols that are knocked up after from the dust blown up. And from this you can have potentially climate change and volcanic winters. You just have too much dust blocking sunlight, and fires, all of which can certainly be quite destructive. However, if we look into this a little bit closer, specifically at the KT boundary, people have looked at the dust layer and decided that it's a bit insufficient in thickness to actually shut down global photosynthesis. There wasn't quite enough dust in the air to prevent light coming through. The global wildfire theory is contested, but there's apparently insufficient charred material. However, despite this, it's still pretty accepted that the KT impact probably had a very major effect on the mass extinction at that horizon, even though there was also volcanism going on at that time. But when we look at other boundary events, if we look at the statistics, basically Chicxulub-sized impactors should have hit every 30 million years or so, which is much more frequently than we actually see mass extinctions. And so if every impactor of that size causes this kind of mass death, we would expect to have seen this much more frequently, which we have not. And also, we just are sort of lacking in the actual impact craters for that correspond in time with the other mass extinction events, specifically for the end Permian and Jurassic. Craters have been proposed for these boundary events, but they haven't really held up to rigorous testing thus far. And so it seems that certainly while an impact could cause a lot of damage and certainly a lot of mass death, it's not really clear that they caused any of the other boundary events besides the KT. So moving on to cosmic rays. An increase, so this is something maybe we don't talk about exactly in earth science so much, but you know, the Earth moves through the solar system, it moves through the galaxy, and there are, on 62 million year cycles, the Earth actually sort of moves north of the galactic plane. And when this happens, it's subject to a lot more cosmic radiation. And so some physicists got a hold of this Raup-Sapkowski plot, which you might sort of vaguely recognize. So this is, now it's the other way around. So this is a long time ago and this is today. But this is the same diversity plot. And they've stretched it out and normalized the curves and everything. And they were able to then fit some oscillating curves to this and see sort of what pattern these, perhaps there are regular periodic oscillations in fossil diversity and abundance. And they find that this also oscillates basically on a 62 million year cycle, which fits well with this movement of Earth relative to the galactic plane. And so the idea then that they have is that it's this increased radiation that we get when we're north of the galactic plane that causes perhaps death and mutation directly, could cause increased cloud cover, which would lead to climate change, and this could be sort of then an astronomical control on life on Earth. And while this may also have serious impacts for life, and certainly the evolution, long-term evolution of life on Earth, it doesn't really address the other mass extinction indicators. So there's a lot of other proxies that we that we find at these extinction boundaries that sort of are proxies for other environmental damage, including carbon and sulfur isotope excursions and ocean anoxia, and it's not exactly clear how this mechanism would explain these other proxies and indicators that we see. Milankovitch cycles have also been brought forth as a possible mass extinction mechanism. And the idea is that it's an astronomical control on the climate variation on Earth. And so because the Earth, the eccentricity and obliquity and tilt of Earth in its orbit changes over time, the distance we are from the sun changes, which is quite a direct control on climate. And this has been shown to explain the Quaternary ice ages, so the most recent ones. And this also occurs on sort of regular cycles, which is then tempting to match up with any regular cycles we might be seeing in the fossil record. And the major effects of this would be glaciation and global warming, and basically sort of climate events pushing one way or the other. However, this is something that definitely has occurred throughout Earth's history and doesn't really necessarily explain the punctuated nature of these events. So extinctions occur quite rapidly, but this is something that's sort of a slowly moving and changing process, and it's always sort of slowly moving and changing. And so, you know, I don't know that it necessarily explains the punctuated nature very well. In addition, the details of the periodicity don't fit quite well. This is a plot that was made quite some years ago, and dates on everything have improved recently, and I'm not sure that this fits quite as well. But so that's Milankovitch. And then finally we have the formation and breakup of supercontinents and their effects on climate and habitat. So once again, there's sort of a periodicity to plate movement on Earth, which could be related to fossil or to life evolution. And certainly from paleogeographic work, we know that supercontinents formed and were broken up over Earth's history. And this could cause a number of, this really affects sort of the environment on Earth and what environment life has to exist in. And so it affects climate change and glaciation, climate patterns. It has the potential to homogenize species, which might make them then more vulnerable to disease or predation, things like this. It potentially reduces ocean circulation because you then have one big ocean in the rest of the planet. And it changes like the availability of shallow marine shelves, for example, but it basically changes the niche space. And so this is something that this could potentially have an impact on sort of the environmental conditions for life. But once again, this is a process that occurs sort of continuously over millions of years, and breakup and formation of supercontinents takes millions of years. So it doesn't really match the punctuated nature of the extinction events. There are more mass extinctions than supercontinents as well. And as many authors actually would argue, it's not necessarily the supercontinent itself that was the killing mechanism, but it's really the associated volcanism that you get when you have supercontinent breakup. So if you see that actually a lot of these large igneous provinces are related to continent breakup. And so really, we now come back to volcanism. So when I talk about volcanism in this case, I'm not just talking about a volcano that erupted, like Mount St. Helens, which was catastrophic and killed things locally. But if we're talking about global mass extinctions, we're really talking about volcanism on a much, much larger scale. The kind of scale where you have volcanoes that essentially fill half a continent with lava and have some kind of horrible fiery storm going on. So large igneous provinces, what are they? So here we have some really nice pictures showing mostly flood basalts from around the world. Some of the most famous provinces, most heavily studied. Large igneous provinces, or lips, are massive crustal emplacements of extrusive and intrusive rocks. So the extrusive would be the flood basalts, like you see here in Deccan, and the intrusive would be sill intrusions, sills and dikes, like we see here in the Karoo Basin. This material is predominantly mafic, and it originates via processes other than normal seafloor spreading. So it's raised many questions about sort of the nature of volcanism and how these sort of provinces can form in the first place, because they're a bit different than traditional volcanoes and seafloor spreading. So lips are found globally, both on the continents and in the oceans, and they've been named a number of different terms in the literature over the years, and they include sort of flood basalt, continental flood basalts, oceanic plateaus, continental passive margins, submarine ridges, seamount groups, ocean basin flood basalts, sort of any isolated volcanics that sort of come in these really large patches just about qualify as large igneous provinces. And I'd like to emphasize that there's also this big difference between sort of oceanic lips and continental lips. And sort of keep in mind when you think about them, that when continental flood basalts erupt, they have to go through continental crust to get to the surface, whereas oceanic lips just go through ocean crust. And all of these, where you can see they take up large portions of continents, and they were in place very rapidly. There's been a lot of studies looking into the details of this, and it looks like most of them were in place on the order of a few million years, or even in several cases less than 1 million years, which for such a large volume of magma is quite rapid. And so to emplace this quickly, this requires large generation of large melt volumes must be generated, and they must be generated very quickly. So studying specific sites in India and in the Columbia River basalts in the US, people have looked at individual eruptive events, so basically individual flows, and they sort of match quite well in the rates per year. About 100 cubic kilometers of material comes out per year, and then they erupt on the order of a few decades to 100 years, a few decades, in this sort of order of magnitude, and you get then a single eruptive event could be as big as 20,000 cubic kilometers, which is quite large. So then lip formation has been attributed to a number of different processes, and this is definitely has ongoing debate today. But the idea is that we need to sort of come up with some mechanism where you can create and melt this much magma and erupt it to the surface very quickly. And so people have proposed mantle plumes, which I think is probably the most popular mechanism. And the idea is that you have this melt coming up from the core mantle boundary, and it reaches the base of the lithosphere and produces these lips. There's also delamination and edge models, which involve sort of magma, either subducted plates melting and dripping in, or magma sort of quickly coming up and around a plate and can melt rapidly this way. All of this sort of requires a fertile mantle. So the ability for the right sort of chemical composition of the mantle so that it can melt quickly. It's also been proposed that meteorite impact could cause lip formation. However, it seems like most of the models don't really support this. There isn't quite enough maybe energy going to the system where you get local melting, but not necessarily enough melting to cause all of the magma we see coming in the lip. So what's the environmental impact of a large igneous province? Well, we haven't seen one erupt, So we have to rely a bit on paleoproxies. But quite a lot of work has been done in this area. And basically, lips are local events with global consequences. As you can see here, there's a number of sort of things that can come out of this kind of volcanism and then interact with the environment and the complex systems on Earth in local short-term scales and in long-term scales. Specifically, some of the local effects include burial by lava and ashfall, poisoning by gases, fire, turbid water, as we see here, water contamination or acidification. And these are things that might affect any region around a volcano, but certainly, they would also affect anything around a lip as well. And because the lip is so extensive, it might just affect a much larger region. Now, globally, there's a number of gases that come out of volcanoes, the major gases being CO2 and SO2. And then you also get halogens. And on a lip, you can just, if you sort of have, say, constant degassing rates from any magma, because you have so much more magma coming out of a lip, you can just generate so much more gas production. And sort of the effects you get from the CO2 include global warming on long-term scales, ocean acidification, and increased chemical weathering. SO2 can result in volcanic winter and light reduction, short-term warming, and long-term, sort of mid-long-term cooling, shorter term than the global warming, but also acid rain. And then with the chlorine and fluorine, you get poisoning and fluorosis and potentially ozone destruction, depending on what else these elements are combined with. And of course, you can also have fires. When you see lava running across the landscape and it hits trees, they usually light on fire, and then that fires can spread across an entire continent, potentially. And this also releases a lot of soot, dust, and ash to the atmosphere. So we see here sort of the effects, short-term versus longer-term effects, where we have sort of this local initial SO2 warming, cooling acid rain and ozone depletion, and then finally longer-term global warming. And really it could be this oscillation sort of between sudden cooling and then rapid warming that could cause a lot of environmental issues as well. So when we look at where the gases can come from in a lip, there's sort of two main ways. One is just the lava degassing itself, and then the other is contact metamorphism, which I'll be talking about a little bit more later today. So if we just look at the numbers from lava degassing, a significant percent of the volatiles in magma actually get vented at the fissure vent. And if they go, basically if the fissure eruption column is high enough, then these gases can get ejected all the way up to the stratosphere. And if not, they remain in the troposphere along the surface. And the gas release is on the order of gigatons, which in the case of CO2 is not that significant compared to atmospheric reservoirs. But in the case of sulfur and the halogens, it's dramatically, like orders of magnitude more than is currently in the atmosphere. And so this can really have a noticeable effect. Now, when we also look at contact metamorphic venting, we have sill intrusions going to sedimentary basins with volatile material that can be volatilized. And we have then explosive release of these gases. We also have estimates that very large numbers of CO2, methane, and halocarbons can be released through this process. So when this gas is released just in the troposphere, so the layer right along Earth's surface down here, and this sort of ends up being this toxic air that the creatures are sort of forced to breathe, but it has more local effects. So if you're in the cloud, then you don't want to be in the cloud on the surface, but it sort of only kills things that are in the cloud. Whereas if it gets ejected all the way up to the stratosphere, which is the second level in Earth's atmosphere, then the gases can circulate globally and have more global climate effects. And so people really look for this when they are trying to find this sort of global impact of volcanism. So if we return to this more complicated chart, we see a lot of this coming out, right? We have the CO2 and SO2 and halogens and dust and ash coming out, and that this interacts, especially the sulfur, on rather short-term scales. And of course, all this feeds back into photosynthesis and primary producers, and things like acid rain, which then directly can cause the death of plants, but also increases weathering, which feeds back into this whole biology ecosystem loop, and say CO2 sequestration rates and things like this. And the long-term effects of CO2 are due to the fact that it takes a long time to draw CO2 down out of the atmosphere and to be taken up by continental weathering. And so this can hang around in the atmosphere and cause warming for quite some time. So now if you look at our specific case study and our lip-induced mass extinction in the case of the N-Permian. So first of all, do we have correlation? Well, we've looked at this a bit before. But we do see a general correlation in time between mass extinctions and large igneous province formation. So the dates here have been getting quite good with a lot of recent work where the Cretaceous Tertiary corresponds to the Deccan traps. And it seems that even before the impactor, the Deccan traps had sort of done a bit of work to degrade the environment already. And the N-Triassic corresponds to camp volcanism in the Atlantic, and the breakup of Pangaea. And then the N-Permian corresponds to the Siberian traps in Siberia. Late Devonian may be correlated to these Villoy traps also in Siberia, but the Endor-Division, it's not very clear whether there are actually any traps associated with this event. And partly when we get to this age, it starts to be hard to date these events, and the rocks are quite old, and so just finding any remnants of them in the rock record gets more and more difficult. But this is basically right here is this line of above 300 million years ago, or sort of in the last 300 million years, we have good correlation, whereas before 300 million years, it gets a bit more unclear. And so this could be due to the fact that we just haven't found the traps or dated them properly. It also could be due to the fact that Earth was a different place back then, and maybe different environmental conditions caused different problems, right? And so maybe just in the last 300 million years, we've become more sensitive to the effects of large igneous provinces. But at least for the last 300 million years, there is quite a good correlation. It's statistically significant, and it seems to improve with the more dates that we get for these lips. Specifically, the major mass extinctions are associated with continental flood basalts, which we would argue studying contact metamorphism is part of the reason is because you get more contact metamorphism with continental flood basalts because you have these sediments that you interact with. And we also see the ocean anoxia events are associated with continental and oceanic flood basalts. So basically when you have any kind of degassing of lips, especially the CO2 that may come out, then this could really at least affect your ocean chemistry. So, do we have plausible causal mechanisms? So I'd like to take a little step back here and sort of think a little bit about what extinction is. And really it requires more creatures to die than are born, right? And that's how we decrease our population rapidly. And I really enjoyed this quote by Rosalind White in one of her papers. There are only a handful of ways to die. It sounds sort of like a James Bond thing, although maybe opposite of what he would say, but when you think about it, you can only die in a few ways, and they're basically listed right here. You can die of old age, you can die of direct physical trauma, you can be starved, you can be suffocated, or you can be poisoned. And everything is sort of permutations on, everything else is a permutation on one of these, so this pretty much sums it up. But if we think about how we can get more creatures to die than are born, then the other half of that, of course, is creatures being born, right? So reduced fecundity, and fecundity is a biologic term about how many offspring you have and how viable they are. So to suddenly have sort of reduced offspring, you can have premature death, so creatures are dying before they're able to reproduce. You can have mutations so that you can't sort of produce viable offspring anymore, even if you don't die yourself. Sort of poor nutrition maybe affects the development. And, other sort of environmental pressures, too many creatures eating you, or, you just can't make it in your habitat for some reason because it's too cold when you come out of your egg or something. So we have sort of these factors that might cause mass extinction, right? So if we think about what environmental parameters and what kind of environmental deterioration would lead to mass mortality and or reduced fecundity. I've come up with this list. I don't know that it's all inclusive, but it sort of at least gets some of the major points. So once again, we have this direct physical trauma that pretty much always kills you. We have loss of light for photosynthesis. And of course, if you lose your primary producers, then that can cause the rest of the ecosystem to tumble. There's ozone destruction causing this mutation, climate change, poisoning, anoxia, and oxygen-poor oceans. If you can't breathe, you're going to suffer. And ocean acidification, especially for marine organisms. If you make a calcareous shell and your shell starts dissolving because the water's too acidic, that's going to be a problem. So if we think then about large igneous provinces and what capacity they have to generate these problems, I've come up with this list. So direct physical trauma, well, that's caused by lava and ash fall. That's pretty clear. Loss of light for photosynthesis. That can be caused by any of these aerosols, ash, or soot that come out of the volcanoes. Ozone destruction, well, it seems to be that halocarbons can be released from these provinces, and so this could cause this ozone destruction. Climate change can be caused both by the CO2 and SO2 release. In addition, maybe to the blackness of the rock covering the surface, changing albedo on the surface, and changing wind patterns and precipitation patterns. There's also poisoning, where we have lots of trace metals and halogen gases that could be either leached out of the volcanic material itself or vented as volatiles, causing local poisoning. There's methane release in global warming, would cause anoxia and oxygen-poor oceans. And the CO2 release, of course, can cause ocean acidification. So we can see here that the lips do have the capacity to generate a host of environmental problems. So for number 3, do we have evidence that any of these mechanisms actually occurred? Well, we can look at proxies in the sedimentary record to determine any environmental change that might have gone on. And when we do this, it's quite pleasing because we see a lot of things happening. So for example, any increase in atmospheric CO2 concentration, and especially any increase in the isotopic value of this concentration, would affect the carbon isotope record. So that's something we can look for. If there's global warming, then that should be reflected in paleosols and the increase, say, in arid flora or animals that can handle desert conditions better. If we have increased continental weathering, this would be reflected in a strontium isotope excursion and also increased sediment supply to basins. If there's ozone destruction, we could see this as biologic mutation and maybe any in any fossils that we have, especially soft-bodied. Increased ocean anoxia is often reflected as black shales and pyrite, a high pyrite abundance, and sulfur isotope excursions showing changes in the sulfur cycling in the water column. Related to this is photic zone euxinia, where you have H2S actually in the water column and high enough up that it can both escape to the atmosphere, the H2S can escape to the atmosphere, but also just disrupt oxygen levels for animals that like oxygen. And this can be reflected in various biomarkers, but isorenaritane is one of the most famous, which is a biomarker for this green sulfur bacteria, which lives in this photic zone right at the line between the oxygen and oxygen-poor zone and basically feeds on this. And then also sea level change and climate change. If that happens, basically we see reflected as lithology transitions in the rock record. So do we see any of these proxy record changes? And we do. So this is the end Permian example here. When we look at sections from around the globe, we see a lot of changes in these proxies. So I'm not going to show you all this data. There are thousands of papers really on this subject. But here's sort of a nice line of plots. Oftentimes so this is from China. Oh, sorry, I didn't list a reference here, but it's from Chao. And we have our geologic timescale here with the boundary right here at this orange mark. And we have lithology listed. And then we have a variety of different parameters. So they're a bit too small to read, but it doesn't really matter. You know, we have carbon, carbonate carbon isotopes, organic carbon isotopes, strontium isotopes, nitrogen isotopes, total amount of buried organic matter. We have a variety of biomarkers. But you can see that basically everything's pretty steady. And then once you get to the boundary, we have lots of oscillating shifts and wiggles and excursions all over the place. And you can see this is a quite a strong mark here. Now there's some The thing to keep in mind, of course, is that it's highly sampled across this boundary, and so if you're going to see any excursion, this is where you're, in a sense, going to see it. But in these places where the samples are more evenly spaced, you can see that there really are perturbations to the system at the boundary event. And so in the case of the end Permian, we see evidence of these environmental changes in the form of carbon isotope excursions, sulfur isotope excursions, strontium isotope excursions, increased pyrite abundance. In a lot of shale sections, we have mutated pollen. There's a fungal spike. This is the supposed fungal, main fungal indicator. We have increase in paleosols and these isorenarotane biomarkers. So from this, okay, we do have evidence for these mechanisms actually having occurred. So finally, fourth, is there a temporal cause and effect relationship between these environmental change indicators, or between actually the mechanisms and the volcanism that happened, and then the environmental change indicators that we see saying that something happened? So to determine this cause-effect relationship relies on a lot of non-trivial rock dating and correlation methods. And there's a lot of details here that we could discuss, but it's not straightforward to measure rocks in different places around the world and then try to figure out how they fit together. So there's different ways we have to do that, and one is using radiometric dating methods. The primary methods are argon-argon and uranium-lead. And this basically relies on the decay constants of certain elements in certain minerals, and you have to find rocks with the appropriate minerals to date these correctly. And so this basically works on igneous rocks. And then we have correlating marine and non-marine sections. It's not always clear which shells in the ocean correspond to what pollen in the land. Luckily, actually, pollen, a lot of it falls in the ocean, and so people can use that as a way to sort of bridge the gap between terrestrial records and marine records. But this is certainly a challenge that's ongoing. And there's also local versus global signals. So just because we see maybe an extinction event in one little basin, does it really mean that everything in the oceans died, or are we just looking at one local sort of natural disaster that may have happened for any host of normal, common reasons? So when we look at the ages of the Siberian traps, which have been measured using a variety of techniques, but I would say sort of the most extensive database is this one here by Racco et al. Using argon-argon ages. And so here they've dated the age of the Siberian traps sort of from top to bottom, in a way, in both the East and West Siberian basins, and compared them to the age of the mass extinction boundary, the official stratotype section for the PT boundary. And this is actually the extinction bed 25, at the end Permian, just before the boundary. And as we see from this argon-argon method, we get pretty large error bars. So one thing is, if we want to see that the volcanism caused the mass extinction, probably the volcanism should have happened first, right? And in many cases, the points do fall before the extinction horizon. There are also points that fall after. But within the error bars, it certainly fits quite well, and so this is very encouraging. There are some funny things, like occasionally the top of the section looks older than the bottom of the section, but this is sort of a natural thing that sometimes can happen. Maybe the mineral that was measured wasn't completely, maybe it was reset, or who knows. A number of things can happen. But the point is that there's a lot of fine details in this dating that still has to be worked out. And then we, of course, are comparing these ages to the age of the extinction horizon, which is sort of shown in this plot here. And it's been officially recorded in Meishan, China, where we have, this is a plot of fossil abundance. So the number of different species, and basically species are sort of coming and going normally, and then suddenly there's a very big line where species disappear. So this is the main extinction horizon. And this corresponds to this negative carbon isotope excursion. And so, very conveniently, this section in Meishan has tuff beds going through it. So these tuff beds have been have been dated, and that's what was used here to provide this age. So these at least can be compared to one another using radiometric dates. So aside from sort of the difficulties in age dating, which is sort of a constantly ongoing and evolving science, there's also, this idea that mass extinctions aren't exactly instantaneous. I mean, they're kind of instantaneous in the rock record, but it depends on what the resolution of the rock record is, right? I mean, everything didn't die in a second and get buried in a second. It happened probably over several thousand to tens of thousands to maybe even hundreds of thousands of years. And so when we look at more expanded sections, such as this floral record in Greenland, we see this. And basically, here we have the onset of sort of the extinction horizon. And up here, we actually finally have the end of the extinction horizon. And in between, there's a lot of different floral changes that can happen and have, say, fungal spikes, which come and then go, and then actually an increase in diversity sort of during this extinction period before we actually sort of go back to this low diversity of the Triassic. And so you can imagine that as creatures start to die, at first that maybe opens up a lot of environmental space and niches for the others that are still remaining. So if the guy that always used to eat you is dead, so then suddenly you have the ability to have maybe many more children for some years before environmental pressures finally take you as well. And so this is another thing to keep in mind, that when we think about this temporal cause-effect relationship, there's probably a lot of different environmental parameters that are going on here. And the big questions are what's actually happening at this horizon that causes these creatures to die out, but then these creatures, well, plants to come back and to thrive for a while yet before they're finally taken. And so it's really this fine scale overturn that we'd also really like to sort out. And significant work has been done in this field, and it has enabled many of these proxies to be brought together. And sort of the biggest sort of timing cause-effect relationship that has been pretty well established, I think, is this relationship between the lithology transitions, the mass extinction, the main event horizon of the mass extinction, and then the onset of volcanism and the onset of the negative carbon isotope excursion. And so at least these proxies, I think, are shown quite neatly here together, where we do have the onset of volcanism at about the same time as the onset of the carbon isotope excursion. Both of these are preceding the actual extinction horizon event. And then volcanism carries on for a while yet, possibly causing a lot of the delay in recovery into the early Triassic. So we have some major cause-effect indicators that have been brought together, but there are also many details that still have to be worked out. And this is, of course, where there's a lot of room for opportunity. And several of the things that we're interested in include sort of this timing of the contact metamorphism relative to lavas. So if we're thinking about gases coming out of these two sources, where and when did these gases actually come out, and how do these rates and volumes compare? How do the emplacement rates and degassing rates compare? So did everything get in place very quickly and then it took a while for the gases to come out, or did everything happen in 100 years, or in 100,000 years, or in 1,000,000 years? And these are when we're thinking about actual sort of death mechanisms. Death happens quickly, you're either dead or you're not. And so sort of trying to nail down all these little steps along the way, it's important getting these overall rates in place. Also thinking about this degassing cocktail, like what gases actually came out, how much halocarbons versus CO2 versus SO2, were there any other compounds that came out that actually were sort of the killing force that we just haven't identified yet, and looking into these degassing compositions. Also, we're interested in fine-scale temporal relation between this degassing and extinction. So as soon as the gas comes out, does it kill you right away, or does it take 1,000 years for it to kill you, meaning that it's not direct poisoning, but really it's the climate change that it induces, for example. And this is, I think, really interesting for the lessons we want to draw for today, for example. If we're releasing a lot of CO2 to the atmosphere, what factors do we really have to worry about? Do we really have to worry about the long-term slow change, or do we have to worry about rapid acidification, or what is really the mechanism that might kill us, right? We think about this relationship between mass mortality versus reduced fecundity. Are we talking about mechanisms that will just straight up kill you, or just mechanisms that will make you suffer long enough that eventually there is, you give up trying, kind of? Also, do we have any proxies for the role of trace metals, and especially poisoning? So poisoning is something that's really hard to look for, I think, in the rock record. We can't really do autopsies in a lot of the fossils, or I don't know, from my perspective, maybe that there's not a lot of soft tissue left, and so a lot of these really sensitive parts are gone, and it's hard to look at. So it's sort of establishing any proxies for these other kill mechanisms. And then also always determining the height of the eruption column. So how high are the gases getting? I know there's a lot of work in our department and around here on these eruption columns, how high they can go, what kind of material they can transport very high up. And this has a lot of implication for how much global warming might have occurred given certain degassing rates and dust production rates. So these are things that we can look forward to working on in the future. So in conclusion, I think I've tried to show that the large Igneous Province induced mass extinction it has quite a bit of support, and it really, I think it demonstrates correlation on a large scale between large scale time correlation. There are a number of plausible causal mechanisms, so it satisfying on this point. We have evidence for these mechanisms. And we also can demonstrate a temporal cause and effect relationship, even on a finer time scale. So in conclusion, I would say that there is strong evidence for causality between large igneous provinces and mass extinctions. Thank you.